Professor Dr. N. Gunasekaran, retired senior professor, after serving about 40 years in Electronics and Communication Engineering Department, College of Engineering, Anna University, Chennai. He is presently working as Principal, Pratyusha Institute of Technology and Management, Tiruvallur, Chennai. He has 40 years of teaching experience in the field of electronics and communication engineering. He had visited countries such as USA, UK, Germany and Sri Lanka on various academic activities. He has about 90 research papers to his credit. He has guided 6 PhD scholars and 3 MS program scholars. He has published 10 books and 10 monographs. He has attended 19 short-term courses. He submitted 33 proposals to the Development of Electronics Department. He had purchased equipments to the tune of Rs 150 lakhs for the growth of the department. He has developed many laboratories such as Microwave Lab, Fiber Optical Communication Lab, Laser Communication Lab, Satellite Communication Lab, VHF-UHF Communication Lab, and UG Basic Laboratory. He conducted more than 50 short-term courses, winter schools, summer schools, and faculty development programs. He executed a number of government-funded projects at Anna University. He received Best Project Awards twice for UG projects at state level through Directorate of Technical Education and at national level President of India Award for the project on telephone for physically handicapped persons. He is a member of many professional bodies such as Institution of Electrical and Electronics Engineering, Fellow of Institute of Electronics and Telecommunication Engineering, and Broadcast Engineers Society of India. He is also a life member of Institution Engineering, life member of Indian Society of Technical Education, and life member of Optical Society of India. His current fields of interest are electromagnetic theory, antennas, satellite communication, and fiber optical communication.
Welcome to UGC lecture series in Applied Electronics. This series covers semester 5, subject 10, antenna and wave propagation. In today's lecture, we will be discussing on different types of antennas functioning at various frequencies and what are their very specific applications. We have been seeing in the previous discussions there is a close relation between the operating frequency and the operating wavelength through the constant c, which is nothing but the velocity of light. The other crucial point we were emphasizing that the signal travels at a super velocity, thereby the whole globe is covered in 0 time. And again, in designing the antenna, what is the design factor? The length. Length is the only design factor in antenna, and the length is taken as lambda by 2. And we have been emphasizing in the previous lecture that lambda is our reference scale. For a communication people, lambda, the wavelength, becomes a reference scale. We no more using the terminology meter, kilometer, like that. Any dimension, system dimension, antenna dimension, wire dimension, any dimension, when we make a mention, we only say it is so many lambdas or so much of fraction of a lambda. Why we are emphasizing this particular reference? Because the moment system becomes comparable to wavelength in dimension, in any dimension, length, breadth, width, in any dimension, the moment the system dimension is comparable to wavelength, it gets a very interesting property of radiating energy. It's a very crucial. Radiating is a very, very unique property of a system when you move into high frequency of operation. Logically speaking, we said wavelength and frequency are inverse related. That what we have been emphasizing in the previous cases. If you see the formula what we have been using, C equal to f lambda and f lambda equal to 300. If f increases, lambda decreases. And if you want to see all the objects around us, which are all in the range of either a fraction of a meter or a few meters, naturally the dimension of the system will be comparable only at high frequencies. Only at high frequency. When I say high frequency, what I mean by that? Maybe running from tens to hundreds to thousands of megahertz. When operating frequency move to thousands of megahertz, hundreds of megahertz, lambda become comparable to meters. When lambda comparable to meters, all the system what we are handling on a day-to-day basis, they may also come closer to the dimension of wavelength and things starting radiating. So radiation is a very interesting phenomenon which we can treat either as a loss or as a advantage. If a conducting wire radiates unnecessarily, it is called radiation loss. If the conductor radiates with purpose, it is called antenna. So that is a point where this antenna philosophy coming to picture. Now we have been already seeing a number of antennas working at various frequencies. In general, the frequency spectrum, the frequency range, spectrum means range, band means range. The frequency band or frequency spectrum is divided into various sections. For example, very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, optical frequency. So there are various frequency bands divided for our convenience. For example, if we say very low frequency 3 to 30, low frequency 30 to 300 kilohertz, medium frequency 300 to 3000 kilohertz, high frequency 3 to 30 megahertz, very high frequency 30 to 300 megahertz, ultra high frequency 300 to 3000 megahertz, micro frequency anything above 1 gigahertz. All these classifications are made for our convenience, because we do use all these frequencies for various applications. Not only for various applications, we are also having a lot of customers in each application. Please understand the need of very wide frequency band for us. Example, when I say I want a band for talking to my friend through telephone, so I need at least 4 kilohertz of bandwidth. Now like me, how many people will be talking to each other simultaneously around the world? Millions of people. So we need bandwidth for millions of people. Next, simple example, television channel. A television channel requires 7 megahertz bandwidth. Today we are already crossing few hundreds of TV channel. So for so many TV channel, I require bandwidth. I have microwave application, I have mobile application, I have a government application, I have a defense application, I have satellite application, I have fiber optic application. Application versus application, lot of application is, they are all there, they are all needing some bandwidth or other, and they are operated at various frequencies. Now why I am telling so many varieties are there, only then we will appreciate that so much bandwidth already there and we already exhausted, we still moving towards optical frequency and much deeper. So thereby we need very wide range of frequencies. Number 2, we also need antennas working in all such frequencies. In that case, we also should know what is the dimension of antenna. Now let us see the HF range. What is HF range? 3 to 30 megahertz. So that is a HF range where you can see the antennas are in the form of wires, long wires. Please again I am reminding you, any conductor can act as a antenna. When I say antenna, what I mean by that? Any conductor is capable of radiating energy. Any conductor will radiate. Whether it is radiating efficiently or not, then I should ask what is its dimension. Whether the dimension is comparable to wavelength. All such secondary questions come at a later stage. The moment current flows through a wire, it radiates. 50 hertz, the power cycle, it is there in our house. We have 50 cycle power supply. It goes to the wire, it radiates. It radiates. The signal going through the local cable operator network, it radiates. Signal goes through TV cable from TV channel to antenna at the second floor, it radiates. So whenever, please take for granted, you can always assume this, whenever current flowing through a wire, it radiates. As I told you, the question whether it is an efficient radiator or not an efficient radiator. If it is efficient radiator, it is called antenna. Now for a HF range, HF means high frequency. For the high frequency range, which is about 33 to 30 megahertz, well, as a communication people, as antenna people, every student without exception should be very confident about the operating frequency. If the operating frequency is forgotten, you will not talk about the proper dimension of the antenna. You don't know what is the application, because based on application, based on operating frequency, antenna changes. Antenna changes totally. If you are not conscious about the frequency, you are bound to make a mistake. HF range, in HF range, lambda is quite large. It is running about at least a few tens of meters. So naturally you see the antenna also running few tens of meters. That is, the antenna dimension should be comparable to operating wavelength. Our antenna code is antenna dimension should be comparable to operating wavelength. So here the operating wavelength also running about a few tens to hundreds of meters. My length of the antenna also few tens of meters. What is it is? Simple conductor. Simple conductor. One end connected to the source, other end connected to a load. That's all. Nothing more, nothing less, no complication. Even if you make a mistake in the length, 1 or 2 meter more, 1 or 2 meter less, still it is working as a antenna. Again HF range, see I written here 3 to 30 megahertz. What is operating wavelength? About 10 to 100 meters. So what should be the length of the antenna? Same size. If you are operating at 30 megahertz, what should be the length of the antenna? 10 meters. If you are operating at 3 megahertz, what should be the length of the antenna? 100 meter. Over. Just measure 100 meter, tie up one end to the source, other end to the load, it works. Radiation takes place. There is a other type of antenna. See, they are all same family, maybe differently oriented. This is a V shape, but it is only a wire. It is look like a rhombus. Each length is a long wire, simply tied down properly, and it is a wire, it radiates. Now this is another beauty. Now we have gone to little more higher end. If you go to slightly higher end of the HF range, then it will come to in the range of meters, as you see in the dimension. Now it is something different. In what is different? There is not one antenna, there is an array of antenna. Now we are entering to another family. We can use one antenna, we can use array of, group of similar antennas. The purpose of going for group of antenna is to get higher directivity, higher gain, higher focusing capability. So when I want to focus energy to a particular direction, when I want to ensure that energy should reach a little longer distance, I have to focus. So that focusing action one will get by going for an array of antenna. An array means group of antennas. it is arranged in a different way. You can see here it is called curtain antenna. The name of this system is called curtain. It is just like a curtain hanging in a window. You can see 1, 2, 3, 4. It is 4 by 4, 16 elements curtain antenna, and this will throw energy perpendicular to the direction of the curtain. If you see next one, Yogi antenna. This is a very common antenna. Practically every one of you having this antenna at home. It is also called an array. Whenever the elements are more than one number, here you can see 1, 2, 3, 4, 5, 6. For example, you can see here, now in this is an array. You can see 1, 2, 3, 4. Still there is a provision here, I can add more number of elements. More the number of elements, it is getting the additional capacity of focusing the energy. So it is called an array. And even if you see the other end also, there also an array is there. Okay. So this is an array, that is also another array. So when you say a system is an array, when the system has got more than one element. This is not an array, it is a single element. This is not an array, it is a single element, but this is an array because it has got more number of elements. This is used as a receiving antenna. We are not actually entered into complication, we are still in a very starting level, we are taking many things in a simple way. For the same purpose, I will give one simple example. For the same application, the transmitting antenna will be looking different, the receiving antenna will be looking different. You take TV Doordarshan, you take All India Radio. What is the purpose of transmitting antenna? It has to throw energy in all the direction. What is called technically omnidirectional. Omnibus. What is omnibus? Bus goes in all direction. So here the antenna is supposed to throw energy in all the direction, called omnidirectional. Whereas what is the receiving antenna purpose? The receiving antenna should look at the transmitter and receive the signal. Follow my point? As a TV receiving person, what is your job? Look, where is the tower? Where is the transmitting tower? So you rotate your antenna and see that it is looking at that transmitting tower, so it can receive maximum. Even when you are listening some noise is coming, you look around and see from which direction the sound is coming, maximum. That you are focusing. You are focusing to receive the maximum signal from the direction of source. But what the source is doing? The source is throwing everywhere equally all the energy. So in this case, in the very specific case, All India Radio, Doordarshan, these antennas are transmitting antenna purpose is different, receiving antenna purpose is different. Accordingly, antenna slightly vary. We are now in the what range? We are in the VHF range. We will see other type of antennas in other frequency operation. TV antenna is functioning at very high frequency. Now why I am emphasizing all these points? Though we give a very common terminology antenna, it is a very big family, very big family, and for each band of frequency things are different. So we should be consciously following where the difference comes. The difference comes when we switch out to different frequencies. Why? Because an efficient antenna dimension is what? What is the dimension, length of an efficient antenna? Lambda by 2. Please remember, these are all you should remember. We will justify why we are choosing little later. So any efficient antenna will have a length of lambda by 2, half wavelength. It is called half wavelength. Physically, what is half wavelength? If you ask, then I will ask what is my frequency. What you are seeing now, it is called a log periodic antenna. Here you can see an array of elements 1, 2, 3, 4, 5. It can go up to 13 elements. Now I will not go into detail, but I will give only one important recognition for this antenna. This is called frequency independent antenna, or other is called wide band antenna. Wide band antenna. Now there is a important philosophy is there behind this. Why we emphasize the word wide band? Because the moment I cut a length, so I cut this, I cut the rod. Now length is fixed, yes or no? Length is fixed. No, I cannot change the length because it is already cut. Once this length is fixed, that means this will have a corresponding frequency because f lambda equal to constant. Once length is fixed, what is the length? Lambda by 2. Whether you say 5 centimeter, 10 centimeter, 15 centimeter, 14, whatever length, the moment the length is fixed, this correspond to lambda by 2. That lambda correspond to one frequency. That means this length will be efficient only for one frequency. I take another, I cut this length. Once I cut the length, what is fixed? Lambda by 2 is fixed because the length is lambda by 2. And this length is maybe let us say about 5 to 6 centimeters. So this length lambda by 2 is fixed. For this lambda by 2, there is only one operating frequency. That means this antenna is efficient only at that frequency. Like that, the moment the length is cut, then frequency is fixed. That means what is the implication? I cannot use this antenna efficiently at more than one frequency. Very important concept. That means once an antenna is cut, the length is fixed, this will work efficiently at only one frequency. That's why it's called spot frequency antennas. It's called spot frequency antennas. But there is a big disadvantage. We are telling so many frequencies, so big band. That means can I make one for every one frequency, one antenna? Then that means I will have millions of antennas I should use. So there are other techniques we are slowly bringing in, whereby how to use one antenna for a small range of frequencies. How to design an antenna to use it for a slightly broader band of frequencies. So those techniques are developed as you go, as you progress. Now here this is called the log periodic antenna. The log periodic antenna is one such antenna where attempts are made to extend the frequency range little wider. That's what it's called wideband antenna. We will see the application later. Actually this is used for television also. For television, log periodic antenna is used. This is a commercial model of log periodic antenna. This is another interesting antenna called helical antenna. It is looking spiraling type. The dimensions are accordingly designed. This helical antenna is used for a very wide range of frequency, including for satellite application. So this is another interesting antenna. The very specialty is it is possessing circularly polarized characteristic. We should know what is polarization, what is circular polarization, what are the other type of polarization, all those things we should study detail later. But just aware, this is another type of antenna which is very unique in nature because it is exhibiting circularly polarized type of waves. The same commercial type of polarization. This is again is what is available in the market, a commercially available helical antenna. Once again a array. See, the moment you see number of elements, you can blindly say it is an array. What is the purpose of array? To improve the directivity, to improve the focusing capability. So slowly certain norms also you are also learning, and by the very look you can always say it is an array, it is a single element, what the type of frequency it is all now you can guess. You are slowly getting that art of how to judge the frequency of an antenna, how to decide an antenna is an array or a single element, what is the purpose of the antenna, whether antenna is a transmitter or antenna is a receiver. So all such things by the very look you can now gauge. I am very sure of it. See, this is another very interesting antenna. Now where we gone? We gone to gigahertz. 10 power 9, we are slowly moving to higher end. We have seen very low frequency, we have seen low frequency, we have seen high frequency, ultra high frequency. Now we gone to the super high frequency, which is a micro frequency. It is gigahertz 10 power 9. You see the lambda. Now I hope you will appreciate lambda now becomes centimeter range. centimeter range. See, at one end we saw antenna length is 100 meters, 200 meters, 300 meters, huge tower, huge mast. Now, what is the length of the antenna? 1 centimeter. I can keep about 100 antenna in my coat packet. I will take another 10 antenna in my shirt packet. So, it becomes so small. Why it is so small? Why it is so small? It is small because we are now moving towards gigahertz microwave. So, what is the general rule now? When you move to a gigahertz range, microwave range, the antenna size is becoming very small, like a dimension of centimeter. In fact, these antennas are called centimeter wavelength antenna. We are giving additional name. If you go to still high frequency, then the lambda become millimeter. So, the antenna is called millimeter wavelength antennas. If you go to still higher range, optical range, the antenna size become micrometer, nanometer. Micrometer, nanometer, our hair thickness. The antenna size will become our hair thickness. Whether we can hold such antenna, we don't know. That's why the whole philosophy changed to lens. Lens concept comes. No more a rod, no more wire. Now, this particular antenna, what you are seeing is called horn antenna. Okay, and this antenna falling under the another new family called aperture. Aperture means this opening. You can see the aperture. Eye opening, eyelid we say eyelid. This is a eyelid is a aperture. So, here is a opening and this is a metallic sheet. It is got the design. These are all done in a proper workshop. It's not easy because the once you go to higher frequencies, the dimensions are very stringent. So, here there is an aperture antenna working in microwave. It is called horn. It is just like a funnel, no horn. So, it looks like a horn. So, it is called horn antenna or aperture antenna, or it is called SHF, super high frequency. Once you go to super high frequency, which is also called microwave range, my size of the lambda become centimeter order. Still Superman, next still higher. So, if you go to 30 gigahertz range, 3 to 30, again we are in the 1 to 10 range. This is a higher end of the gigahertz. Then we call another type of aperture antenna called a reflector antenna. Today, I don't think anybody would have missed the dish antenna. So, this is like this dish antenna. Now, this is still smaller, but this type of dish, everybody would have seen the dish of the 1 meter size, 1.5 meter, 2 meter size, and cable operators are also using dish antenna. What size? What size? Can you say what is the size of the dish antenna used by cable operator? 12 feet, 16 feet, 20 feet. So, and again the point you should remember, when the size of this antenna, these are all thumb rule. As a thumb rule you should remember, you will appreciate when you go around the city. In the dish antenna, this is called dish. Dish is a word, commercial word, not a technical word. Technical word is a reflector. It is a reflector. You can see a reflector. The signal reflected by this reflector surface and get focused. So, this are called parabolic reflector antenna technically, and when the size of such antenna becoming larger and larger, the gain is enormous gain. The one antenna where you get the highest gain is reflector antenna. Please remember, whenever you come across such a very big dish antenna, in fact, Doordarshan, commercial, all these professional antennas, the All India Radio using dish antenna, your Doordarshan using the dish antenna, the BSNL people using dish antenna. So, those dish antennas are exhibiting very large gain of the order of 10,000, 100,000. That is, the focusing capability is so high. We call that beam coming out of it called pencil beam. So, pencil beam, that means it will go from one dish to another dish. It's called line of sight communication. It is like this. This is called line of sight communication. Over one tower, one dish will be there. It is like this. You can see this is a one tower having one dish. This another tower having one dish. It is called tower to tower communication. This is called tower to tower communication. And this is also called microwave link. Microwave link means this system working at microwave and they are transmitting or communicating from one tower to another tower. Now can you guess a complication in this? Can you guess? Because this become a dish, a reflector, the beam will travel as a narrow beam. The beam will travel as a narrow beam. If the beam travel like a narrow beam, then they should be in exact height. Exact height. So here more than the electronics, the civil work is very complicated, because you are, please understand, you are trying to focus, you are trying to align, two dish antennas at this height. What is the height of the tower? It may be about 30 meters, 40 meters, sometime above the hill. Most of the time it will be above the hills. So focusing one dish antenna from one hill to another dish antenna to another hill is not an easy joke, because if the line of sight is missing, signal gone. It's not that 50% signal, 20% signal, it's not a bargain. Once the alignment is even missing even slightly, total signal is gone. So when you go to higher frequency, this difficulty is there. So all your satellite communication, micro communication, tower to communication, they are all falling under the line of sight communication, where system design becoming more complicated. But what is the biggest advantage? What is the biggest advantage? Enormous gain. Gain of the order of tens of thousands, hundreds of thousands, like that. So today we have seen different varieties, different structure of antennas working at high frequency, very high frequency, ultra high frequency, micro frequency and tower to tower communication. You would appreciate it that as you progress in frequency, the lambda becoming from meters to centimeter to millimeter, the lambda becoming smaller and smaller. And what is one more beauty you should have been observing, as lambda becoming smaller and smaller, the gain of the antenna is increasing. Okay, so we will see the further some more type of antenna before we start exactly how antenna functions. Okay, we will meet, and the question you should be today, you will be clear is, what is a general observation as you progress in frequencies? Why micro antennas are showing higher frequencies? What are the civil type of complication involved when you go to micro frequencies? And how further higher frequency is going to be more complicated? So such questions are now clear, and at least one thing you should be very clear, how there is a progressive change in the structure of the antenna, in the construction of the antenna, in the property of the antenna. They are all improving as you go in a higher frequency. That means the conclusion we are making is, an antenna engineer, an antenna student should be very conscious about frequency. He should be very conscious what frequency he is talking, what is the frequency at which the antenna of our interest is involved. Thank you. We will meet again.